All right. Well, hope everyone had a happy Easter weekend. Um, Apparently, out of the 32 people who were supposed to show up here, 12 of them felt that that long weekend was not long enough. I'm so taking attendance today. All of you who are watching and instead of being here. And um, we have still a fair amount to cover. So every day, significant material is going to be covered until we get to the last week where it's review and getting started in the final. So I'd recommend being here. Okay. Um, all right. Um, yeah, I graded everything that I had anyway. Mostly problem set 11. Also, there were some 10s in there. And I'll just keep getting things back graded as I get them. So, trying to think of any particular comments that I had about. Well, actually, I'll hold off on that until Wednesday, when hopefully there are more people here. Yes, I'm pissed about that. Okay. So, today we get the new chapter. It's chapter 4 in both the text and the notes. Higher order equations. We spent the first part of a course on first order equations. We've spent a lot of time lately doing second order equations, and now we'll do equations of any order. Now, whereas there seemed to be a huge difference between how we handle first order versus second order, although it's not really as different if you look at it from a linear algebra point of view. Here, we have no choice but to have some linear algebra, and we see that there's actually very little difference in terms of the approach you take for solving higher order equations versus second order. So that's why I can get through this material relatively quickly. In fact, we do have a method on undetermined coefficients, but there's really literally nothing new to cover with that. The method is exactly the same. We'll just do some examples so you can see that for yourself. There is variation of parameters. That has to be generalized because you're dealing with larger matrices depending on the order of the equation. But what you did before second order, characteristic equation, finding the roots, etc., all of that generalizes in a straightforward way. But before we really get into this, I need to handle a notation issue. Because typically in whatever class you're taking, if it's calculus involved in it at all, you normally deal with only first and second derivatives. But since we're going to move beyond that, we need a workable notation. Because if you're just dealing with first and second derivatives, primes are fine. You can do y prime, y double prime, and y triple prime is not so bad either. But once you get down to like fourth order or more, and you have lots and lots and lots of primes, especially when it's small print on a page, you're like, is there really a fourth or a fifth derivative? And certainly anything beyond that at that point it's just silly. So, for derivatives of order higher than 2, we're actually not going to have a bunch of primes. The notation we use instead is for third derivative, y with a superscript of 3, but put in parentheses. The parentheses are very important because if they're not there, you're going to think, oh, it's y cubed, and that's definitely not what we're looking for. Y4, Y5, etc. So different people use different conventions. Usually, I think it's a good idea for derivatives of higher order 3 or more to go ahead and use this notation. And really, you can use it for any derivatives. It's perfectly fine, as long as it's easy to tell what derivative you're talking about. Also, for consistency, because I'm going to be describing certain general equations in terms of this notation for whatever order derivative, even first or second, or even no derivative at all. So y superscript 0 in parentheses, you're not differentiating at all 0 times, so that's just y. So that'll be important to keep in mind when I, that C doesn't really look like a C. All right. When I describe general equations where I need to use this kind of notation throughout. So the general rule is the derivative with respect to t, assuming dealing functions of t, or x, y is written as that. You may have seen this notation before, like for instance in Cal 3, where to describe Taylor series. I'm sure you have fond memories of Taylor series, showing a converge and all that good stuff. Okay. Oh. I know I have something else in here to get back. Oh, okay. Okay, so with this convention in mind, now I can write down what is a equation of general order. Okay. So we're just going to focus on linear, just like we did second order equations. Mostly constant coefficients. All right, so we have the hyperderivative yn, and we normally write the equation in such a way that it's by itself. It doesn't have a coefficient. And if it doesn't, you should divide by it up front. And then also remember you did that, as some people have forgotten. And then some coefficient, which I'll call P1. So I'm going to use P as a subscript for any coefficients that we have. So we have P1 for n minus first derivative, P2 for the n minus second derivative, and so forth, all the way down to Pn minus 1 with the y prime, and then Pn with y. So one thing to keep in mind is, if you look at the index of P and the order derivative, they always add up to n. And then we have some right-hand side g of t, like we did before. Now, the first order equation, we had a single initial condition. For second order equation, we had two initial conditions, one on y and one on y prime. So for nth order equation, it follows we have n initial conditions. So we have y of t naught equals, and the way I normally describe these initial values is, I've always done that. Y prime is y naught prime, y double prime, the t naught is some value y naught double prime, and so on. And then we use the same parentheses notation. So we go all the way down to the n minus first derivative, whatever that is, at your initial time t naught. So all initial conditions are specified as some initial time t naught is y naught n minus 1. So those are given values to narrow it down to a unique solution. Okay. Now, we're going to see that the way you come up with a general solution is a straightforward generalization of what we saw with second order equations. using characteristic equations and so forth. Once you have it written down and you have your constants, C1, C2, etc., up to Cn, you have to solve a system of equations like before to satisfy initial conditions. Now, the thing is, now you're solving for n values. You have a system of n equations in n unknowns. So the linear algebra is going to be more of a pain. So if I write down the general solution is going to have this form: C1y1 plus C2y2, and so on. That looks familiar. So Cn, whoops. I should identify that as y of t equals all this. Cn yn of t, that's your general solution of your homogeneous problem. Plus, if it's non-homogeneous, you're also going to have a particular solution. If not, then you can just say this is 0. So, all of these, as usual, determined by your initial conditions. And when you go to find those constants, that satisfies this tedious system of equations. So we have C1 y of t naught plus C2, wait, y1 of t naught, C1 y1 of t naught, C2 y2 of t naught, and so on, up to Cn yn of t naught. And that has to equal y naught. And if you have a particular solution, that should be subtracted off after evaluating that at t naught also. And when you had initial value problems for non-homogeneous equations, effectively that's what you were doing. Whether you wrote it that way or not. And then you have more equations, for instance, on the first derivative. So you plug in t naught into the first derivatives of all of your n linearly independent solutions. And it keeps going all the way down to the n minus first derivative. So you have n unknowns, C1 up to Cn, and then you're going to have, you need n equations to nail them down. And that's what these are here. Minus the n minus first derivative of your particular solution if you have one. Okay. Now, fortunately in problems we would only get to generally third and fourth order equations. Occasionally you might have something higher order. I think the highest order I've seen in any homework problem is sixth order. Okay. Now, the thing to address is when can the system of equations be solved? Now, for second order equations, the answer to that question was when the Wronskian of y1 and y2 is non-zero. So we're going to define a Wronskian for nth order equations, so it would be the same thing. This system can be solved if and only if, for any initial values you have, if and only if the Wronskian of y1, y2 up to yn is non-zero. So, Okay. Yes, I'm taking attendance now. Okay. Now, for all these solutions that we find, y1 to yn, to be as before, second order equations, a fundamental set of solutions is necessary for them to be linearly independent we must have the Wronskian of y1, y2 up to yn, which is defined to be the determinant. That's what this vertical bar notation means. The determinant of, now you remember Wronskian for two equations, you had y1, y2, y1 prime, y2 prime, and then you took the determinant of that, and that was pretty straightforward in that case, and now this just generalizes. So you have all your other solutions along the first row, their first derivatives along the second row, and then second derivatives along the third row, all the way down to the n minus first derivative of each in the last row. So to make sure your solutions are linearly dependent, you would plug those in, or you may have be evaluating them at a particular time to see if you can solve for initial values at that time. In variation of parameters, you need a Wronskian as a denominator in integrals. That will happen again for higher order equations. So like if an n-fold order equation, you have n integrals, and the Wronskian is a denominator in each one. And unfortunately, you have a similar determinant for the numerators also. So yeah, it is going to be painful. And yes, there will be a problem like that in the final. You have been warned. Okay. Now, I want to point out, well, actually, no, I'll hold off on this until I get to examples. I want to make sure I get through today is how do we get, at least for constant coefficient case, how do we get the solutions y1, y2, etc. up to yn in the first place? And even though it's a straightforward generalization of what we saw for second order, of course the algebra gets more involved. There are certain things, complications that would not come up with second order equations that can come up with higher order ones. Okay. All right. Okay, so constant coefficients. So same form of equation, except now all the coefficients, P1, P2, etc., are constants. And for the time being, we'll assume that there's a homogeneous equation. We'll deal with non-homogeneous ones probably on Wednesday. Okay. So at the start, you proceed just like you did in case of second order equations. You find your characteristic equation. In the exact same way, that order of differentiation becomes a power of your variable. So we have lambda to the n plus p1 lambda to the n minus 1 plus p2 lambda to the n minus 2, and so forth, all the way down to pn minus 1 lambda plus pn is 0. So go ahead and fork that, and by whatever means necessary, you compute your roots. The thing is, how are you going to do that for higher order polynomials? The answer to that is we use nice cases. Because I'm not going to give you something where you have no idea how to factor, but you have to keep your factoring techniques in mind. Just as an example, what's one technique that you likely learned long ago for factoring a cubic? Hopefully, at least some of you remember. What? You can always use division, but there's something in particular for cubics that's nice. Oh, well, that's what he was referring to, I think. But something that's a little friendlier. Grouping, factor by grouping. That ring a bell for anyone, please? Yes. Okay. So that's going to be useful in certain examples. Also, sometimes the coefficients can be recognized from Pascal's triangle. Does anyone remember Pascal's triangle? Okay, we're going to review all this when we get to certain examples. But so these are 2 arrows you want to have in your quiver. Okay. Once you have the roots, and again, it can be real or complex or repeated. Okay. So here are the cases. So if a certain root, lambda I, is real and it's distinct, then you have, so if it's one root standing alone from all the other roots, it's not the same as any of them, then you have your exponential, like before. Now, you can have repeated roots, and they can repeat any number of times, up to n. Now, what happened before, you have your exponential. Okay, actually, we're going to stick with real roots here. I'll deal with, you could not have repeating complex roots before in a second order case, because you get any complex root, its conjugate had to be a root, and that'd be different. But with higher order equations, you can have repeating complex roots, and I'll get to that momentarily. So if you have a real root that repeats k times, you have your exponential, and then your next solution would be t times that. And that's what you remember from the second order case, but then it keeps going. So the next solution in your fundamental set of solutions is t squared. And you keep going. So if a root appears k times, actually, I'm going to try to avoid some ambiguity here. Because if I say repeats 10 times, you might think it's a total k plus 1 occurrences, the first one, and then k repetitions, but it's not what I mean. In your set of n roots, this one shows up k times. Right? So you have k solutions altogether. So you keep going all the way up to t to the k minus 1. So for instance, if a real root of 2 appears 5 times, then you're going to have e to the 2t, t e to the 2t, t squared e to the 2t, t cubed e to the 2t, and finally t to the 4 e to the 2t. So all powers of t from 0 up to k minus 1 for a grand total of k solutions. Okay. Now, if we have complex roots, alpha plus or minus I beta. Now, just like before, they have to occur in complex conjugate pairs. So we have yi is e to the real part times t times cosine of imaginary part times t. And then similarly, e to the real part times t times sine imaginary part times t. So that's where you have two complex roots, and then those complex roots, either one of them repeats. So in this case, of distinct complex roots. But the last case is, what if you have complex roots that repeat? Really, you're putting the last two cases together. So you still have your exponential times the same cosine or sine, but now those are multiplied by the appropriate powers of t. Okay. All right, so if you have a situation where alpha plus I beta and alpha minus I beta, they occur k times each. So in other words, you have 2k roots total that we're talking about. Then you have the same roots as before, same solutions as before, exponential times cosine and then sine. And then your next solution, pair of solutions, is all that times t. This continues. Oh, that's strange. Okay. So t squared e to the alpha t cosine beta t e to the alpha t squared e to the alpha t sine beta t. And what's really awful about this is because it's satisfying initial conditions, or if you use this for method on determined coefficients, because you have to use product rule to differentiate that. Now you have, that was enough of a pain with these solutions, and now you have these powers of t also. So this keeps going all the way up to t to the k minus 1 e to the alpha t cosine beta t. And then sine. Now, don't get hung up on the subscripts I wrote here. You just have to keep in mind that you have n roots, once you account for how many times roots repeat, and then you're just going to write down n solutions, and here's where you get them for all the different cases. So as long as you have, for an n-fold equation, you have a grand total of n solutions formulated using these guidelines, then you're good to go. And I don't really care like how you label them, like y2, y1, y2 up to yn. Okay. So now I'm going to, yeah. All right. show you some examples of how we handle characteristic equation and how we get to roots. So you think of this as a review of some factoring, since we haven't really touched anything beyond a quadratic lately. Okay, so the equation, the first example is the third order. So y triple prime, or we want to write as y 3 with parentheses. Don't forget the parentheses. Okay. So this is your third order equation to start with. So what is the characteristic equation?
Lambda cubed minus 2 lambda squared minus lambda plus 2.
Yeah. Okay. So now, how can we factor something like that? Yes, that's why I mentioned that earlier. For grouping, see what you can factor, if anything, out of the first two terms. So what can you factor out? So ignore these. What can you factor out of the first two terms?
Lambda squared.
Squared times lambda minus 2. And then what you can do is you have minus lambda plus 2 over here, but you can write that as minus this. Minus lambda minus 2. So now you can factor a lambda minus 2 out of everything. And what's left, so if I write that here, so what goes here?
That's lambda minus 1.
Or lambda squared minus 1. Yeah. But now what can you do with that?
You can find what lambda is.
Someone else said, yeah, difference of squares. Yeah. So lambda minus 1, lambda plus 1, lambda minus 2 is 0. So, what are your three roots? And 2. Okay. All right. Sometimes, especially on tests, I would still see difficulties with getting your roots from some quadratics, even after they were factored to a certain point. So hopefully that's just due to time pressure in a test, because that's something that you guys ought to know how to do by now. Okay, so now we have 3 distinct real roots, and we need to write down 3 solutions, and don't really care what order they're written in. So what would solutions be in this case? Real roots. Just like second order.
1, C1, and 2
Sorry, what?
C1, you can
Oh yeah, but right now we're just looking at the solutions themselves. So yeah, so we don't need constants yet. E to the t. And what else?
The negative t.
And
2.
e to the 2t. All right, so these make your fundamental set of solutions for this equation. So all solutions in this homogeneous equation are a linear combination of these. So the general solution is, now you bring in the constants, c1 e to the t plus C2 e to the minus t plus C3 e to the 2t, and you're done. So if there were initial conditions, then you would take first and second derivatives of these to form a system of three equations for three unknowns, C1, C2, C3. Right. So any questions about how to get the general solution in a case like this? Okay. Well, that wasn't so bad, but don't worry, it gets worse.
So much better.
Well, we're just tiptoeing it. The point is, by the time we get to the end, even though it does get worse, you can still handle it. That's the idea. Okay. Let's look at another. So fourth derivative, minus y equals 0. Or it might be better to write it this way, or in parentheses, to indicate fourth derivative. Okay, so what's the characteristic equation this time?
R to the fourth minus one.
Yeah. Okay, and what can we do to start factoring that?
R squared plus one, R squared minus one.
Okay, so the difference of squares there. Okay, and how much further can we go, at least by keeping it real? We can factor a little more.
R is equal to
Yeah, this one can be factored further. R minus 1, R plus 1. Okay, so for our roots, we have 1 and minus 1 so far as roots. What are the other two?
plus minus I.
Yeah, so I and minus I. Okay, so we have our four roots that lead to our four solutions. So y1, y2, y3, y4. All right, so what would those roots be in this case? What's the solutions be in this case?
E to the t, e to the negative t, e to the,
No.
then just a repeat e to the cosine.
Nope.
No.
Cosine and sine. Now, if you started, if you continue to say e to the, that would not have been wrong unless you actually gave it a non-zero exponent, because it's e to the real part times t, but the real part is 0. So if you caught yourself and said e to the 0, then that would have been fine too. And then times cosine and sine of the imaginary part times t. The imaginary part in both cases is 1. So for these roots, alpha is 0 and beta is 1. So you get cosine t and sine t. So now we can write down the general solution. So constant e to the t plus constant e to the minus t plus constant cosine plus constant sine. And you're done. Unless there are additional conditions, of course. At least these solutions would be easy to differentiate. Well, actually, the ones from a previous example would too. But if you have repeated roots or more interesting complex roots, then you have to be careful with a product rule in that case. All right, so any questions about these for getting the general solution? Actually, I'm trying to remember. I took for instance, for higher order equations on the final. Well, keep in mind the final is comprehensive, so there will be some of the old things, like first order equations and so forth. But most of them, well, actually, a little more than half will be about new stuff. Stuff this week on higher order equations, and then Laplace transforms, which I work on next week. So in a moment of mercy, in the final, there are a few problems involving higher order equations like this one, but I never specified initial conditions. I just said get the general solution like this. But there's also ones that I'll start covering on Wednesday that are non-homogeneous, where you have to use the same old methods from second order, undetermined coefficients, or variation of parameters. There's one other thing that comes up factoring-wise. This would be let's see, actually a couple things. That could come up. There, again, what do you want to have in your arsenal? Okay. Okay. I mentioned this one a little while ago, Pascal's triangle. So you have one at the top, and then two ones down below, and then each, you have ones going down the sides. And then each number in the interior is a sum of the two directly above it. So 1 plus 1 is 2, and then you add these to get 3, and then you add these to get 4, add these 2 to get 6. And you see a pattern of the coefficients that emerge. These are also binomial coefficients. So if I number these rows, so n equals 0, 1, 2, and so forth. And if I indicate positions like j equals 0, 1, so always starting from 0, across each row. So the number in row n, position j is, what are those called? Anyone know? Of a formula that gives you these numbers. They definitely come up in other classes, probability for one. Binomial coefficients. So n factorial over j factorial, n minus j factorial. And when j is equal to 0 or n, it's always 1. If j is equal to 1, or then it's always equal to n, and so forth. Okay, so that could come up, that these multiply the coefficients. So for example, if I have the characteristic equation lambda to the 4th minus 4 lambda cubed plus 6 lambda squared minus 4 lambda plus 1. So those are the exact coefficients over there, except alternating in sign. So lambda is equal to minus 1, repeated, recurring 4 times. So the idea is these numbers are the coefficients of lambda plus 1 to the nth power. So if, like, for instance, you have x plus 1 squared. Quantity squared is x squared plus 2x plus 1. If it's x plus 1 quantity cubed, it's x cubed plus 3x squared plus 3x plus 1, going from left to right. Well, actually, it doesn't matter because it's symmetric. And if they alternate signs, then it's lambda minus 1 to the n. So if you see this kind of pattern recognized as a row from Pascal's triangle, then you can get the factorization that way. So that's one case that can come up, like on homework problems. And the last case I want to mention, something like this. Lambda to the 6 minus 1 is equal to 0. So you're taking basically the 6th root of 1. So you can tell that, for instance, 1 is a root and minus 1 is a root. But really the way you want all of the 6 roots of 1, also known as the nth roots of unity. So what you do is if you go around your circle, starting at theta equals 0, which means that lambda is equal to 1, so that is the obvious root, then for whatever n is, you chop your circle into n equal parts. So in this example, 6. So here you have pi over 3 for each pi slice, and they're all supposed to be equal. So your roots are actually equal to, lambda is equal to cosine of j pi over 2 pi over n plus I sine j times 2 pi over n for j equals 0, 1, up to n minus 1. So those are this is a formula. This comes from complex analysis of the all the roots of 1. So what will happen is, in the case of lambda to the 6 is equal to 1, lambda is equal to 0, and then you have cosine pi over 3 plus I sine pi over 3. Then you have cosine 2 pi over 3 plus I sine 2 pi over 3, cosine pi plus I sine pi. But you should know that cosine pi is equal to minus 1 and sine pi is equal to 0. Whoops, sorry, my first root is supposed to be 1, not 0. Theta equals 0. And then you keep going. So you have cosine 4 pi over 3 plus I sine 4 pi over 3 and cosine 5 pi over 3 plus I sine 5 pi over 3. So you get 6 distinct complex roots. 2 of the roots happen to be real. But whatever n is, you're going to have n roots, and they're all arranged that way in a nice equidistant manner around the circle. So that's how you can write down all the roots in that case. So for this case, you'd have 2 real solutions, e to the t and e to the minus t, and you'd have 4 solutions involving exponential sines and cosines. Okay, I know I'm past time, so we'll on Wednesday.